We said that this has 2 turning points. Again, this is not in your lecture notes today, but I just thought I'd take it out for Monday. And the polynomial regression that the curve that we fit to that looks something like that in Monday's lecture notes. So from the 2 turning points, you know that your minimal degree is going to be 3, your smallest possible degree for modeling this, okay, is 3. So you go to your calculator, and if you had your data, you'd put your data into L1 and L2 or L3, L4, and you would come down here and you would ask it to perform a cubic regression, because that's degree 3. If you thought your data would be best modeled by a parabola, the shape of a parabola, you would ask it to do a quadratic. If you thought maybe something higher than cubic, you would use a quadratic. Now, the only next thing you have is logistic regression, and exponential regression, and power regression, and then logistic. So you don't have anything higher than quartic for a polynomial. Okay, so we will be doing some of these regressions later towards the end of the class. Notice you have 2 linear regressions. I don't know if you ever noticed that. The first one, they do the same thing. The only difference is the order of the addition. And in algebra class, since we're so used to seeing mx plus b, we use this first one. But when you take a statistics class, statistics will always start with whatever your y-intercept is. They call that the starting point. And then you add or subtract from there based on your slope. So they always start this way. You get exactly the same numbers, the same exact R value. It's just what different classes use. That's the only difference between 4 and 8. Okay, so let's take a look at our first data. So pull out your calculators, please. And we'll review the steps. And if you have forgotten the steps, the end of these lecture notes, if you look at the end, has all of the steps written out for you, okay? On the next to the last page for polynomial regression. Does anybody not have a calculator? Okay, you can go to my office and get the bag, okay? So just, it should be right when you walk in straight ahead, you'll see a little black bag. Just pull one out. Bring the whole thing in, Shane, in case someone comes that doesn't have a calculator. Okay, so the data we're looking at here is the number of women in the full-time civilian labor force in millions, that's our unit, with children under the age of 6. So if you were looking at this data, what would you tell me about this data? Just from looking at it, what would you tell me? What would you tell me, Austin? It's increasing. It's steadily increasing. That's all we can tell. We don't know the rate it's increasing. We don't know. It certainly doesn't have any turning points. That's one thing you notice, right? It doesn't have any turning points. But what would you say about the difference between the rate of increase? If you looked at the average rate of increase between 1975 and 1980, and you compared it with the average rate of increase between 95 and 2000, what would you tell me about those 2 rates? The rate of increase between these 5 years and then these 5 years. It's what? Greater. It's greater, right? So it's the average rate of increase, and the number of women in the workforce, the rate is decreasing, right, in those last 5 years. So the question then becomes, well, I wonder what happens after 2000. And actually, I have the data for that. I just put it up to 2000, but I have the real data because I think it took me to like 2011 when I looked this up over the weekend. Okay, so where would we start? Well, we always start with putting the data into our calculators, and you can call it list 1, list 2, list 3, list 4, whatever you want. But remember, when we work with this data, God bless you. When we work with the data to keep our numbers small, especially our constant value, you want to use something like let t equal the number of years from 1970 or 1975. Most of the time it will be up to you what you want to use as your starting point. So I've just chosen, I could have chosen any year I wanted. I just decided to start with 1970 because I could do my subtraction pretty easily. So right above each one of these years, 1970 is going to have a t value of 5 because it's 5 years from 1970. Then what would the next one be? 10, keep going, 15, 20, 25, and then 30. Okay, so now I have all of the values I'm going to enter into my calculator. And just as a little review, you hit Stat, and you have your first button is Edit. You hit that. And then you go to L1 or L2. I happen to enter mine last class into L3 and L4. So you enter 5, 10, 15, 20, 25, 30 into your first column. And then your second column, whichever one you're using, you enter 4.851 million women, 5.886. All right, you just put those in. And when you're done with that, let me know. I don't want you to do anything beyond that. I just want you to put those data points in. What type of regression, a model would fit your data? You need to see it. So remember, you want to go to your stat plot, which is the button above y equals. So you hit second y equals, that brings us to stat plots. You want to make sure only one of them is on. So if you see more than one on, shut one off. So I'm just going to go to the first plot, and I'm going to go down. I'm going to hit enter. I'm going to turn on. And remember, it's this first picture that's your scatter plot. And then you just come down here and you tell it what are the names of your two lists. So I happen to have L3, L4. If you have L1, L2, that's what you put in there. And then before you hit graph, do you remember what zoom number you hit for statistics? Zoom 9, right. So you hit zoom and you hit 9 because 9 is zoom stat. Once you hit the 9, you're going to see your graph. Oops, you're not supposed to see all that. That's still on there from my first class. Okay, let me turn those off for a minute. Okay, so let's just hit zoom 9 and you see your scatter plot. Okay, does this data right now, does it have any turning points? No, so you would probably say no turning points, 0 plus 1. Linear regression would probably be pretty good for this. So that might be one choice. But as you look at your data, you say, and after that question I asked you earlier, you're saying, boy, the rate of increase is starting to slow down. Look, it was increasing pretty steadily, and look, it's starting to slow down. Does this just kind of continue to increase forever and ever like this? Real slow? Does it continue to increase a little bit and then start to decrease? And if so, a parabola might be a really nice fit for this. I wonder what would be the best model. So we're going to try both of them. We're going to try the line of best fit, and we're also going to try a parabola of best fit. So we're going to try a linear regression and a quadratic. Now, don't worry if you miss any of the commands because they're all written out for you as I go through them. But I also want to draw your attention to something over here. How do we compare models? How do we know which model is the strongest or the best fit? Well, when we were just doing linear regression back a few weeks ago, we looked at the R value. And if you recall, your projects had you find data that had an R value, the absolute value was bigger than 0.6. But remember, your R value only tells you the strength and direction of a linear relationship. Linear, that's all it tells you about. So if we're going to be looking at quadratic models and cubic models and possibly quartic models, there's not going to be an R for those. So there is a measure, a statistic called R square. And for everything other than your linear regression, the R is a capital R. And for your linear regression, it's a small r. You can use your R square values for all of your regressions, and then you compare those. R square, the closer it is to 1, the stronger it is. Your R square values go between 0 and 1 because you're squaring it. There's no such thing as negative R square values. So very similarly to our R, the closer and closer you are to 1, the stronger your association, the better your fit for your model. Okay, so let's take a look at the equation for the regression line and the equation for our parabola. Now remember, folks, our regression line is going to look like this. It doesn't have m anymore because we're a polynomial. Shane. Well, maybe they're in your phone that you've been looking at. Okay, so A is acting like your slope, okay? A is the leading coefficient, what we've been calling the leading coefficient of in our polynomial form. It's also our slope. So if A is positive, we know our slope's positive. We know our right hand's up, our left hand's down. If A is negative, if our slope is negative, our right hand is down and our left hand is up. For our quadratic equation, it's going to look, they're going to use the letters A, B, C instead of A sub 2, A sub 1, and A sub naught. A here is still your leading coefficient, okay? So in both of these calculator models, A is the leading coefficient. Okay, so let's take a look at, let's try to recall the steps we go through so we can plot our line of best fit and then our quadratic regression. So recall that we hit the stat button, we go over to calc, and we go down and say we want to do a linear regression. We hit enter. Then we tell it where the data is. So mine is second 3 because that's my L3, comma, second 4 because that's my L4. And then I tell it now, where do you want me to store the equation? I want the equation for my line of best fit to be stored in Y1. Remember, we have to go to our vars button, hit that, scoot over to Y-vars, hit enter, and then hit Y1. Okay, now when you hit enter again, you'll get the values for A and B, which is your slope and your y-intercept. Okay, there they are. So it says write the equation of my regression line. Here's my equation. Y hat equals 0.211074287 x to the first power because I'm linear. And then what's my y-intercept? 3.99186 repeated. So this is saying that if x is 0, that would be back in what year if x is 0? What year would I be back in for x is 0? 1970, because that's my 0 year. It's predicting that there was about almost 4 million women in the civilian labor force who had kids under 6 years old. So from 1970 to 75, it increased by 800,000 women. Then it went up about 1 million in the next 5 years. Okay, and then almost 1.5 million in the next 5 years. Okay, so this is what our data is telling us. You go to your R square value, and it's a pretty high R square. It's 0.959. Okay, so there's our linear. Let's take a look at graphing that. Again, you hit zoom 9. And you look at your straight line, and geez, a straight line is looking pretty darn good for 75, 80, 85, not too bad for 90 and 95. The year 2000 seems to be the furthest from that line, and the line is just going to continue at the same rate. What is that rate? It's 0.2 million women every single year. That's what the slope tells us. About 200,000 women every year is being added to the workforce. So the question is, how comfortable would you be to try to predict with this model the number of women after the year 2000? That's where you have to kind of check in with your comfort zone. So you say, well, it looks fairly reasonable. I'd be pretty confident with that. But let's look at the quadratic. So let's do the same steps. Can you help me? Let's see if we can jog your memory and help me with the steps we do to get the quadratic. So one at a time, you can tell me what steps I go through. So I want to get a quadratic regression now, not a straight line regression. Second, stat. I'm in stat. Where do you want me to go to calc? Mode? Oh, you just want to get me out of, all right. Second mode, there I am. Stat, you could have just gone to stat, but that's all right, okay. Adam's turned off, you can't talk anymore. Now what? Go to calc, yeah. Quad regression, okay, boot is turned off. Second 3, yep, comma, and second 4, comma. Okay, Beth's turned off. Vars, vars. You can tell me one more. Y vars, okay. Someone else? Enter. And we already have a straight line in Y1, so we might as well keep it there if we're going to be comparing them. So Y2. And then what do I do? Enter. And now I'm going to get all the information I need for my parabola. Mary, you want to join Adam and Kate? So when you work together, you can work together? Okay, so what's A here? A is negative. So my leading coefficient for my parabola is negative, which tells me I have a sad parabola. Okay, which means I'm going to have a maximum point at some point according to this parabola. B is 0.3799242857, and that's my coefficient for my x value. And then my constant term is 2.8662. And what's my r square value? 9.8. It's even better. I mean, excuse me, 0.9859. Okay? So when I now look at the graph, would you expect that it's going to be closer to all those actual data points than the line itself, the line of best fit, or not as good a fit? What do you expect from looking at your R square values? It's going to be better, yes, because R square is better. So hit zoom 9. Don't forget zoom 9. There's your line, right? And now let's see what the parabola does. Whoa, that's pretty nice. Okay. So notice your parabola is not slowing, it's not slowing down. I mean, it is slowing down, the rate's slowing down, but it hasn't started its turning point yet, right? It looks like it's going to continue to increase at least a few more years before it starts to turn downward, right? Okay, so let's get a picture of this and put it in the notes. Oh yeah. The picture. Scoot it down here in the notes. Zoom 9, you need zoom 9 for all of this, yeah. Just throw this right down here. Here we go. So now, as you know, we want to use our data, our lines of best fit and our quadratic regression to help us maybe with a prediction. Our data set goes out to 2000. We'd like to see what the line would predict for 2011 and what the parabola would predict, the parabolic model. And this is, so first you have to say, okay, what t value do I put in for the year 2011? What would be my value of t? 41. And how did you get that? Yeah, you say 2011, take away 1970, because that's what I'm starting, is 41. So you would put 41 in both of these models where you see x. That's a pain, but your calculator can do it all for you with your table set. Woo woo, yay, let's do that. Let's get the calculator out. Where'd the calculator go? Oh, here it is. Nope, that's the recording. This happens a lot. I have to close it and then bring it back. Now it comes back. I hope it's still there. It is. I was going to say, I hope it still has all the data in it. So it has these equations in Y1 and Y2. So you set your table. You're only interested in the year 1941. So, well, you could start with the year 1940 if you want. Now you want to ask your table for a particular year, or you could have it automatically increment. It's up to you. I'll just keep it on automatic because I know my second value will be the year 2011. I hit second table. And right here at 41, if I go down to 41, this is what each model predicts for the number of women in the civilian force. My linear model predicts that there will be 12.646 million women, and my parabolic model predicts 10.333 million women. Again, not knowing much about what happens after 2000, I would be fairly confident with both, but it looks like the quadratic regression has a slower increase, and it looked like my data that the number of women with children under the age of 6, that rate of increase was starting to slow down. So I might be a little more confident with my quadratic regression. Well, let's take a look at the actual data. Here's the actual data. Okay, let's see. Can I make this bigger? I don't think so. Oh, yeah. No. All right, so 2011, women with children under the age of 6 was 10.403 million. So it's actually a little bit lower than what we predicted, right? So let's take a look at what happened after 2000. 2000, we reached a peak at what, 2001 of 10.4 million women in the labor force, and then it starts to decrease, increase, decrease, increase. Okay, it's kind of going up and down a little bit. We actually reached the peak in 2007, and since 2007, we've been pretty much within the same general area. Okay, it's right around, just around 10.5 million women. Okay, so when we look at these models, we've got to be very careful about going too far outside of our data set. Our data set takes us to the year 2000. We can be pretty confident if we want to estimate, in between these years, like if we wanted to find 1983 or 1992, we could be fairly confident, very confident about the estimate. Let's look at your R-squared value for both of them. That's called interpolation, right? Interpolation is when you're within the boundaries of your data set. When you go outside, even if you went outside and you did like 1970, so if we tried to predict 1970, look what each model would tell us. When X is 0, it says in 1970 there were 3.99 million. And what does the quadratic tell us for 1970 when X is 0? How many women were in the data force for this particular model when X is 0? 2.8. So let's actually see the real data again. Did I close it up? Oh, I hope I didn't. I think I did. Let me open it again. Okay, so 1970. Oh, this starts in 75, so we can't go back. All right, that's okay. So anytime you go out too far outside, you could have model breakdown. And in fact, the end behavior for your quadratic model has a leading coefficient of what? Negative 0.004, blah, blah, blah. That's A sub 2. That's your leading coefficient. So that tells you that as time goes to infinity, the number of women in your workforce, Y, is going to go to negative infinity, which we know is an impossibility. So at some point in time, I don't know how far out we're going to go, it's going to actually predict a negative number of women in the workforce, and that's when we would eventually get model breakdown. Okay, eventually, model breakdown. So you've just got to be careful when you use these models how far outside your data set you go to make predictions. Okay, any questions on anything that we've done for this particular example? either finding the line of best fit or the parabola of best fit, quadratic regression. You have this is not in your textbook. So the only homework and practice you can get with this for any assessment that you're going to have, both your quiz after the next one, your next test, and your final, is to work through these problems. So working through I think I gave you 4 data sets. Working through these 4 data sets will give you plenty of practice that you need to answer anything you might see on a test or a quiz, okay? So you have the rest of the hour to work together and work through these questions and these data sets. Get used to this process all over again. Use your flag if you need help, and Shane, I'll help you with your data set. And try to get as much done today as possible. Oh, I did forget to say one thing, folks. I have a plead for you. Every single lecture I put at the end to do the preview questions for the next section before coming to class. I'm almost begging you to please do number 110 on page 364 before class on Wednesday. It's a very simple question. It's just a long division question. Arithmetic. Okay, I want you to do it by hand and review long division before you come to class on Wednesday, because on Wednesday we're going to be doing it with polynomials. Okay, and so life will be a lot easier for you if you review the process with arithmetic. Okay, so have fun with these data sets. I think some of them are interesting to look at.